Hey everyone, this is Dr. Walker. This is video 92 on the Doppler effect. I wanted to go over this topic because it's a good application of sound that you are probably familiar with. Have you heard an ambulance go by you and you hear the pitch of the siren sound higher as it approaches you and sound lower as it goes away from you? Well, if so, then that's the Doppler effect. It's an apparent change in the frequency of the sound when there's some kind of motion between the source of the wave and the observer. Let's examine why this happens. Let's consider an observer that is moving towards the source of sound. So we're using S for the source and O for the observer. The source is emitting a sound wave. It's propagating in all directions. These blue lines here are the wavefronts. So each wavefront is one cycle of a wave. If you're moving towards the wave, then instead of having one wavefront hit you every second, you're going to have more wavefronts hit you every second because they're going to reach you sooner since you're moving towards them. So that's why when you're moving towards a source, the frequency appears higher. The opposite happens if you're moving away from the source. Now you're going to hear less cycles per second because they're going to take longer to reach you because you're moving away from that source. So the frequency appears lower when you're moving away from the source. We have an equation that we can use to calculate the frequency that we observe compared to the frequency of the source. So again, O is for the observer and S is for the source. So if we know the speed of the observer right here, if it's moving towards the source, we use a positive. If it's moving away from the source, then we use the negative sign. And V, that's the speed of sound. So we're either adding or subtracting the speed of the observer from the speed of sound. We plug it into this equation and that will give us the observed frequency F sub 0 or F sub O. The Doppler effect works in a very similar way if it's the source that's moving, such as the ambulance moving, rather than the observer. The equation is simply reversed with the velocity of the source here being at the bottom. The V here is still the speed of sound. If we're trying to find the observed frequency, then we're going to subtract the speed of the source if it's moving towards us, or we're going to add it if it's moving away from it. What's going to be the result if the source is moving away from us? The result will be that the observed frequency is going to be lower. If the source is moving towards us, then the observed frequency will be higher, just as we expect. And we can see that by plugging in some values, and we will do that in the guided example that follows this video. But first, I wanted to show you the general equation that it's possible that both the source and the observer are moving at the same time. And we can combine the two equations to get this general equation, which can be simplified to this form, whichever form that you prefer. If the source and the observer are moving towards each other, then you just use the upper sign on the numerator and denominator. If the motion is away, then you just use the lower sign. And that will give you a higher or lower frequency as you would expect. Let's look at one question. It says, does the wind affect the pitch of a factory whistle you hear on a windy day? This one's a little bit tricky. What do you think? You might be thinking, well, that wind might be pushing the sound toward us faster, so maybe we're going to hear a higher pitch. But the thing is, the source is not moving, and the observer is not moving. So usually there's going to be a change in the observed frequency of the sound if the source or the observer is moving. What's happening here is that the medium is moving, right? The sound is traveling through the air, through this wind. The medium is moving. How does that affect the pitch? And the answer is it actually doesn't. I have a good analogy that I found to explain this. Think about this conveyor belt, and let's say that you're putting an item on the belt every second. Can you see that if this person puts an item on the belt every second, then this person will receive an item every second as well. And let's say it's a slow belt. Now let's say if we have a fast belt. So now the medium is moving faster. That's like the wind blowing. Well, if the person is still depositing an item every second, do you see that the person is still going to receive an item every second? The only difference is that now, because the belt is moving faster, it means that they're going to be spread further apart. But you're still going to get the same number of items per second. So you're still going to have the same number of cycles per second or same frequency of the pitch. Let's look at another example in the video that follows.